this lesson, we're going to look at the solution process, and we're going to look at it qualitatively and then also look at it quantitatively. So first of all, I'm going to start with a couple of definitions. Solvation is when a solute particle is surrounded by solvent particles. And then hydration occurs when that solvent is water. And so that's what we're going to be mostly looking at in this lesson, is hydration. So the ability of a substance to disperse uniformly throughout another to form a solution depends on two factors. The first is the fact that mixing is the natural tendency of substances. They tend to mix with one another, and that's because they are increasing their entropy. Entropy is a concept that we'll look at in the next lesson. It's simply a measure of disorder. And so the tendency is towards more disorder, and there's more disorder in a solution. The second factor that influences the ability of substances to create a solution is the types of intermolecular interactions that occur. And there are actually going to be three that we look at that affect the energetics of solvation. The first one is solute-solute interactions, and those must be overcome, meaning energy is required. So it's going to be endothermic. Then solvent-solvent interactions, which must be overcome, which again is going to be endothermic. And then finally, solute-solvent interactions must occur, and those are going to be forms, and so as a result, it will be exothermic. Heat will be released. So let's look at the energetics that's involved. So really quickly, just to review, here you've got sodium chloride, salt dissolving into water. Your solute-solute interaction is the breaking of sodium and chloride ions. Your solvent-solvent is the water molecules breaking from one another, that interaction being broken. And then the solute-solvent interaction is the sodium ions and the chloride ions being hydrated, being attracted to their solvent, which is water. So let's look at the energetics. So the enthalpy of solution equals the change in enthalpy of the solute plus the change in enthalpy of the solvent plus the change in enthalpy in the mixture. So let's actually look at what each of those terms means. So for the enthalpy of the solute, that is the energy that must be provided in order to break the solute-solute interactions. So you can see that there, it's going to be endothermic, meaning that the enthalpy is positive. The solvent-solvent interactions must also be broken for the enthalpy of solvent, therefore it's also going to be positive and endothermic. And so the enthalpy of mixture, the solute-solvent interaction that forms, that is going to be negative. It's going to be exothermic. So when you add those together, so the enthalpy of solvent, enthalpy of solute being positive, and the enthalpy of mixture being negative, if you look at the left-hand side graph, notice that the change in enthalpy of the entire solution is going to be negative because the enthalpy that's released in the mixture of the solute and the solvent, that is greater than the two enthalpies that are required to break the interactions. So that would result in a solution that is exothermic, meaning if you dissolve that salt or whatever solute you have in that solvent, heat would be released and you would feel hot. Now, for the other type, again, you're looking at enthalpy of solvent plus enthalpy of solute. Notice here that the enthalpy that's released when the solute and solvent interactions occur is going to be less than the sum of the two other enthalpies. So as a result, the overall solution process there is going to be endothermic, meaning that energy is required, and therefore what you would feel when that solution is formed by that mixing would be cold. So this solution process, the energy that's involved, this should pique your interest because you actually use this often whenever you use a cold pack or a hot pack. If you're using a hot pack, it's a hot pack because the solute-solvent interaction is stronger than the enthalpy of solute plus the enthalpy of solvent. If it's a cold pack, then the enthalpy of mixture is going to be less. What we're now going to be looking at is calorimetry. And the first type we're going to be looking at is constant pressure calorimetry. And what we use for this is a simple coffee cup calorimeter. And so what we can actually do is measure the amount of heat that is either absorbed or released when a solute is dissolved in a solvent, when you make a solution. So we can actually put some numbers to this now. So what you have to keep in mind is that the heat that the solution, that water solution, gains is going to be equal to the negative heat of the reaction, because what we're assuming is all of the heat that that reaction releases is going to be absorbed by the water. We're assuming that the styrofoam cup serves as a perfect insulator. It doesn't, obviously, but that's an assumption we're going to make. The other equation we're going to use is Q equals mc delta T. Now, Q stands for your heat, M stands for your mass, C is your specific heat, and then delta T is your change in temperature. So what you'll be able to do is, using your mass, specific heat, and your change in temperature, you can measure the amount of heat that's either absorbed or released in a solution process. Now keep in mind, change in temperature is your final temperature minus your initial temperature. So let's look at an example right here. It tells me I have 6.50 grams of solid sodium hydroxide, and I'm going to dissolve it into 100 grams of water. Now, it wants me to determine the heat that is going to be released, and I know it's going to be released because the temperature of the water is increasing. And so what I'm going to first do is I'm going to use this formula to determine the heat that the water, that the solution absorbs. And I can do that by saying, all right, Q equals my mass. Well, the mass of the entire solution is going to be 106.50 grams times the specific heat of water, which is 4.18 joules per gram degrees Celsius, times my change in temperature. Now, my change in temperature is my final temperature, 37.8, minus 21.6, which gives me 16.2 degrees Celsius. And so when I find my heat of my solution, that is 7,210 joules. Now, I know that my heat of my reaction is simply going to be the negative of that, because while the solution gains 7,210 joules, my reaction releases that. So it's going to be negative 7,210 joules. What I'm going to do now is I'm actually going to convert that into kilojoules, because it asks me for kilojoules per mole. So it's going to be negative 7.21 kilojoules. And now what I need to do is I need to get into kilojoules per mole. Well, what I can do is I can say, all right, negative 7.21 kilojoules is released when 6.50 grams of sodium hydroxide is dissolved. Well, I want to figure I can figure out per gram. I want to figure out per mole. And so what I'm going to do is I'm going to convert that 6.50 grams into moles. So I'm going to divide by its molar mass, which is 40.0 grams, and that gives me 0.163 moles. So what I can do is I can take negative 7.21 kilojoules and I can divide that by 0.163 moles, and that will give me kilojoules per mole. And so my final answer is negative 44.2 kilojoules per mole.